So I would like to begin with an improvement of something we proved yesterday. Okay, an improved, let me just call it an improved bound. An improved bound. And no, I'm not sharing, 1 second. So yesterday we proved, 1 minute. Yeah. Yesterday we proved the following thing, that 1 plus 1 by n to the power n is less than n. Right? For n, for n big enough. I mean, not big enough, and just n bigger than equal to 3. Is that right? Yeah, yeah. So Unab, have you seen the proof of this, or have you tried to prove this? It was. So did you understand? Did you understand? Did you get it? Okay. If you didn't get, then I can explain it again. Yeah. Yes. 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 So Ishana, can you tell us maybe, or just we can try together if you get stuck in any case, how we proved this? Yes, yes, that was certainly there, but like the proof, how did we, like, you can tell us one of the methods which you are most comfortable with. We kind of did it in two ways, I mean solidly. So one of them you can tell, or this is the same as obviously this. Exactly. So you were basically saying we did an expansion of this. Right, right, exactly. So that's the simplest method, right? And Una, you know the binomial theorem. I think you would know the theorem, right? Yeah. So just use the binomial theorem. I mean, yeah, Ishana, I think doesn't formally know it, but we kind of did it, right? So basically, yes, I'll not go into the thing again, how we did, how we got the expansion, but we know it either through binomial theorem, or we can just use reasoning. So if you do the expansion, then you know that you will get right. And this you will certainly have practiced also binomial theorem. So this is expansion. Now you see, so this is what we want to prove, this final thing. Now this is very simple, right? Because if you take n choose k, and then what is n choose k? It goes like this, divide by k factorial, right? So now this is certainly less than n to the power k, right? Because in place of n minus 1, you can take n. In place of all these things, you can take n, you get n to the power k. And you can forget this. It only becomes bigger, right? So just to say it more clearly, this is less than n times n k times, right? And this is again k factorial. So this is equal to n to the power k by k factorial. And this is obviously less than n to the power k, right? So n choose k is less than n to the power k. And this is also a very simple fact, right? If you just think by logic. Yeah, this is the number of ways to choose k people from n people, right? And this is, can anybody give a meaning to n to the power k? Combinatorial meaning? So n to the power k, can anybody give a combinatorial meaning, meaning some problem whose answer would be n to the power k? Like n choose k, we know choosing number of ways. I should write number of ways to choose k people. And what about n to the power k? So it's like, this is n into n. So can we think of a problem where n to the power k would be the solution? So, well, you can think of it like there are k places. Yeah, there is no choosing, but this is much simpler because this is just like multiplication principle, right? It's there are n places, there are k places, and let's say there are n items, right? And you want to place them in k places, and you can place the same item again and again. Right. Then for each place you have n choices. Right. So you can also think of it like there are n people, and there are k designations. And you want to give this k designations. You want to pick a k, you want to give these k designations to some people here. Right. So obviously for every designation, there are n choices and options for every designation, because you can give the same person several designations or all designations to the same person. Is that right? So then certainly this is n to the power k, and this is then more, right? Because it's like it's something like one person can be chosen more than once, but in this problem, one person is chosen only once, right? So clearly this is less, right? And in fact, you know that this is, you can say it from here also. So you can say it in several ways, right? That this is less, even this is just common logic. Okay, so then you see the problem is almost done. Then the problem is almost done because, okay, yeah, can anyone complete the problem from here? What should be done next? Sorry. Yeah. So what should we do next? Now that we know that n choose k is less than n to the power k, so how can we use it here? Hmm? No, k cannot be n plus 1. So n choose 1 is equal to n choose 2 is less than n square. How can we use these things? So these things we have. So the hint is that you have to just use it in the simplest way. It's kind of just putting the value of n. It's like just replacing n choose k by n to the power k. This thing. Absolutely, yeah, right. Exactly. That's right. So you see, n choose 1 times n to the power n minus 1 is less than equal to n to the n times n to the power n minus 1, right? And then n choose 2 times n to the power n minus 2. See, just in the simplest way you have to use, right? N choose 2 is less than n square. So just use it, right? And that's it. So basically, yeah, this is what Ishana is saying, that each term is less than n to the power n. So Unab, is this okay? Okay, right. So you see, just in the simplest way, okay, n choose 1, I'll just, this is less than n. This is less than n square. So just use it in the simplest way. Then you'll get that each term is less than n to the power n. And we can ignore the 1 in the end. Okay. Right. And then you can add them up. Just add them up. So just to complete it, this is n to the power n, this is n to the power n, c. And now just add them up, you get n times n to the power n, which is simple. So this was pretty simple. We also did it by induction, but let's not go into the details of that now. So you can review that. Induction is also something that you would have done formally. Is that right, Unav? Have you done induction? Yeah. So yeah. So then you can follow that proof. Try to see it again. Okay, in case you can't do it. So induction was the other way. But yes. Right. So that also I've discussed in the video. First, to try it on your own. Okay, try it in this form, and if you, because it's a little tricky, and if you can't do it, then see it, and then you can ask me if needed. Okay. Okay. So this is something that we proved. But I had also said this in the class and yesterday, and this is maybe you would have seen. I think Ishana has not seen it, but maybe seen that as the value of n increases, as you go along the sequence, it's a fact, and we will not prove all that now, but it's a fact that these numbers are not just less than n, but these numbers move closer and closer to some number which is called e, which is given a name. E is a name that is given to that. Okay, this is a fact. So do both of you see that this is much more stronger, this statement, right? That this is less than equal to e, right? Than this one. This, what we proved, this is like a baby version of that, right? Which was much easier to show. But e is just a symbol given to this limit, but we will not go into the limits because we don't know that concept yet. But we can't prove it is less than e maybe now, or less than equal to such a, maybe if I say 2.8, but I think we can prove the following. I think we can prove it is less than 3. So this is my aim for today, trying to prove that this number is less than 3. Okay, and the technique we will be using is expansion again. So once again, this is an improved bound from yesterday, but the technique is going to be similar. Prove this and using expansion. So first take some time and try to think about this. Take some minutes and then we can step by step go. You can think of some other way also if you can get. Try it. So once, sorry, my mic was off. Once again, my plan is to use the binomial theorem. Okay, using binomial theorem. So let me just state it because both of us know the statement, but let me still state it. Okay, so 1 plus x, I'll just write it like this, is equal to, so we can write it both ways, but let me write it like this. No, let me write it like this. 1 minute, sorry. Yeah, I'll just write it like this. X. No, it doesn't actually get smaller. This gets bigger. As n increases, this number gets bigger and bigger, but it still remains less than 3. That is the magic. And it's kind of intuitively clear that it doesn't blow up. But yeah, we will use this. And now this, if you don't, and even if you know the binomial theorem, try to, try to kind of convince yourself that this is true by using the simple, how many ways you can get x, how many ways you can get x square. Just convince yourself using that. Okay, that's the same thing as binomial theorem. So we will try to use this. Okay, so let's see what happens if we use it here. Let's see. I don't know. I have not proved it like this before. Let's see. So what will be the first term? Just 1, right? What should the second term be? There is no x here. If, I mean, right, so what will that be? That is just 1. Yeah, so it is this, but it is just 1. So that is a little, that's interesting in some sense. Okay, but we will see. Yeah. Then you have the next terms are clear. Just put the values. I mean, just put the values in place of x. And you can put, okay. So you see, we have already proved something interesting here. 2. This 2 is already here. So this means that we have already proved it is bigger than 2. And this itself is not simple to prove if we don't use binomial theorem. Okay. Yeah, I mean, you can check for n equal to 1 and 2, but it is that doesn't prove it, right? So we have proved that it is bigger than 2 for any n, even if n gets bigger and bigger, is bigger than 2. So at least that we have proved. Now let's think about the rest. Okay, let's think about the rest of this. The ideas are very similar to what we have done earlier. So I'm not doing something suddenly very different. Sorry. I will just. Any n. So in the previous question, it was similar, but we just had in place of 1 by n square, we had n square. And in place of 1 by n cube, it was n cube. So, and we want to prove that something like the same, like less than kind of thing. Sum of all the, yeah, but that is not good enough. Right, but that will not be good enough. Will it be good enough to show it's less than 3? No, right? But yeah, you would have shown it is less than n or something, right? Yeah, or maybe better than that. But 3, but yeah, that's a good observation. So what Shana is saying is simply that, like simply what we had done, n square times this may be. Am I right? Is this what you're saying, or you're saying something more tight? Like this is less than n cube and so on. So Ishana, is this right? Is this what you're saying or something? Okay, you're saying that. Okay, that is correct. Is that okay? Yeah, but that will not be, yeah. But if you use this, then all you can get is less than n. But this is not good enough. But again, you have to just do the analysis more carefully. Like last time we had kind of wasted the k factorial. If we don't waste it, then what do we get? That is the thing. Okay. Let me write a hint. If you want, you can use it. Sorry. So you can use this. And this is something that we have done earlier. You can prove this. Okay, let's just assume it for a second. You can do it later. No, I mean, it's just dot dot dots. So I mean that no matter how many factorials you take, it will be less than 3. So you can just take it till n by 1 by n factorial only. And this you may have seen or may not, but for a second we can assume this. So from here you should get the hint of trying to prove that this is less than 1 by 2 factorial. Is this less than 1 by 3 factorial? Question mark. Can we prove it? So can we prove this? I mean, last time we showed this is less than 1, but now we are showing it's less than 1 by 2 factorial. So it's better, not just less than 1, but less than 1 by 2 factorial. So just write the definition of n choose 2 and you should be able to see it. Right. Write the definition of n choose 2, n choose 3. The algebraic definition. One by 2 into in the denominator. Okay. Okay. How did you get this in the denominator? Wait, okay. Let's write that. So it's n factorial, 2 factorial, and minus 2 factorial. Okay. No, but if you cut it, and then there is n square, right? Yeah. Yes. So then you get n into n minus 1 by 2 into n square, right? No, but that is not correct. But no, wait. Okay, but see, that's the same thing. You can check it, right? Yeah. You see, that's the same thing. I mean, you can check it as this. Right, and then you can cancel this, right? And then you get this, right? And this is certainly less than half. Now this is less than 1. This we already know, right? So that's basically maybe what you did, maybe some different way or some slight error, calculation error. But I mean, you can just directly use the definition, right? This is also the other equivalent form, right? After cancellation, you can say it like this directly. but it's same thing. You will not lose anything. Maybe just takes a few more seconds to get this, okay, by cancellation. Right? So then do you see that in the same way you can do the rest, right? If you do this by n times n to the power k, 1 by n to the power k, then you do this. And then it's simple that this quantity here is less than 1. Does everybody see that? Yeah. And then that's it. Then this is less than 1 by k factorial. You see, last time we just ignored the k factorial. We kind of didn't use it. But now if you use it, then you get less than 1 by k factorial. Okay. Okay. So then it's, so you see, it's just the same method, but just a more closer analysis. Okay. So let me remove this. I'll just keep this manipulation here. So it's a very simple thing. So you see each term here n choose k times is less than 1 by k factorial, right? So basically what have we proved? We have shown so far that 1 plus 1 by n to the power n is less than 1 plus 1 plus 1 by 2 factorial. Well, this first two terms you can write 0 factorial, 1 factorial, but yeah. And then you get 1 by till n 1 by n factorial. Is it okay? We have shown this just by using the binomial theorem and simple comparisons. Now, if you use this, that no matter how many n's you take, this quantity is less than 3. Like it doesn't depend on the n. Okay, you keep taking like the 1 by 2, 1 by 2 square, 1 by 2 cube, right? And no matter how many n's you take is less than 1. So in the same way, this is less than 3. If you use that, then you're done. Okay. Should we try to do this? Yeah. Let's try to do this, okay? Let's try to just see this quickly. But if you assume it, then it's clear, right? Is it okay with both of you? Okay. So it's very simple. Okay. Any questions? Okay. So then I'll remove this. We have proved a very important result, and this is between 2 and 3. And for any n, it is between 2 and 3. So now we try to prove this, right? What we will show, let's do it fresh. So, and here we will use the factorial inequalities related to factorials and powers, which we had seen. So we will show that 1 by 0 factorial, 1 by 1 factorial, and so on, no matter how many n's you take, this will be less than 3. Okay, maybe I should write for any n. Okay. So yeah, anyone, if they have done, or you can think of some way to show this. This is much simpler. You have to just compare it with something. Yeah, 0 factorial, you would have seen maybe in the books that it is defined to be 1. Right? 0 factorial is always defined to be 1. Or maybe you have not seen, but the definition of 0 factorial is 1. Reasons can be given. Some philosophical reasons can be given. but this is a convention. Okay, to begin with, it is a convention. And the definition of n factorial is that from 1 to, you multiply from 1 to n. But yeah, this does not meet that convention. It doesn't meet that rule because then it would be 0. But yeah, there are some reasons which I don't want to go into now. I'll say that later. But there are good reasons why it's not defined to be 0. You can understand. It's kind of like counting and so we can just write it as 1 only. That won't make any difference. Just 1. So try to compare it with the powers of 2. And maybe that can. Can we say? No. Numbers are getting closer and closer to 0. It does not mean that the sum will get closer and closer to 0. Right. Yeah, this topic was there. I had done this very earlier. In that time you were not joined. Yeah, but yeah, we will obviously see it. So the numbers are decreasing. Sometimes the numbers are decreasing, but the summation doesn't. That summation still blows up. It goes to infinity. So again, here we will be again using a fundamental inequality, which we had done. We will use this. N factorial is bigger than 2 to the power n, or maybe I should say k factorial is bigger than 2 to the power k. Yes, right. After some time. Yes, right. Or you can say. Una, do you have any ideas? Will be greater than 2 raised to 1 by 2, or 1 by 2 raised to 2. Right? No, less than. Sorry, I'm trying to say less than. See, there's no use in putting a lower bound, right? There's no use in saying this is greater than something because we eventually want to prove less than. So take that into account. So let me write a few more terms and see. So can we like try to use this inequality? This all of us agree, right? Okay. So how can you use this? So you can use it like, see, you want to use it in a way that 1 by k factorial, 1 by 3 factorial, 1 by 4 factorial goes on the lesser side. So if you use it, then what do you get? Right. You get this is less than 1 by 2 cube, 1 by 2 to the power 4, right? 1 by 2 to the power n. Is this fine? Right? So this is again similar kind of thing, term by term comparison, but by using this. Now, sorry, this, that's fine. Yeah. 1 minute. So, no, so it is not true. This is not true. Yeah. Like this, right? We can just write this. It is okay to write this. And this is this true? Yeah. No, this is, it is not true. Yeah, that is not true. So no problem. I mean, we can just put a square here, right? Yeah. and then we can, after some point it is true, but in any case, you understand. I mean, it's come do it with powers of 2 basically. You can, yeah. But then the point is that you can see this just by a picture, or if you know the geometry progression formula, or you can just see this intuitively that this is less than 1, right? Because it is half, and then it is half of the remaining, and then half of the rat remaining, right? This is less than, and this you can see it in many ways. You can understand. So then this is less than 1, and we already have 2 here, but the total is less than 3. Okay, so comparing with the geometric series is a fundamental technique. This is called the geometric series. Okay. Um, Unab, I will ask you to maybe review these classes. Okay. We had done these techniques. This was like the first, one of the first or second problem we did, right? So try to review that. If you don't have, I will send you the recording. And yeah, so Ishana has not done this. Maybe Ishana can also watch this if she gets time. Okay, but I will do it formally definitely later with. Okay, that's but yeah, but this is a simple technique. Okay, but it has numerous applications. This technique. So, anyways, it all starts with this very simple bound. So then we are done, right? Our problem is complete. So we have completely proved today that this number is less than 3 and it is bigger than 2. Okay, with simple methods we have done. The methods you've seen along the way, you should, yeah, keep them. Okay, any questions? Yes, so basically in terms of limits, you can say that when n goes to infinity, then this becomes 3. The limit is called e. And yeah, basically the limit of this is, yeah, but that is later. Usually people just do it without understanding. They just have this and extends to infinity or whatever they do, and then they just memorize this limit is e, and they use this. That's how it's done in J. Because proving that this limit exists is not so simple, but at least we have proved that it is between 2 and 3. Okay, but whether it goes closer and closer to some fixed number, we have not yet shown that. Okay, but we have used the techniques earlier to prove till here so far. Okay, so today I'll just end a little early, but I will give a small homework which you guys can try, and we will pick up from this the next day. I plan to do some combinatorial type of inequalities, which also are asked, are popular in exams. I'll do that next time, but I'll also give that homework. So please note this down, or you can see it in the video later, but you can just note it down. So I want you guys to show that this is an increasing sequence. What do I mean? I mean, you know what I mean, but just to write it clearly, I want you guys to try to prove this. Again, we have proved similar statements. Think about this one. As n increases, this number actually increases. Okay, now it is not so obvious, right? Because the inside the bracket it is decreasing, on the top it is increasing, but intuitively it's the right that it should increase because the power has more effect and so on, you can say, but still it needs a proof. Is that right? Still needs a proof. We have proved a similar thing, but we have not proved this so far. Think about this. This is it's fundamentally important to prove that it will have in the end have a limit. Means it will go closer and closer to some fixed number and won't behave in a haphazard way. This increasing is kind of there, but you will just do it as a problem, as a challenge, as fun problem. One. And the second, show, number one, show that 1 plus 1 by n, 1 minute. maybe you can do this, to the power n is a decreasing sequence. So what do I mean? I'll just check this. Then I mean this is bigger than. Again, you can cross multiply, simplify, and then try. It's up to you. I want you to show this, but just give me a minute. I'll just check it quickly. Because I might be wrong. I just not able to think completely clearly, so I'll just check it. But at least I know that there is one of them which increases and the other side decreases. So the limit kind of gets sandwiched in between, which that will be clear later on. But let me just check it. One second. Right. Just to be, this might be wrong. I just correct it. This is a decreasing sequence. Okay. So is this correct? Because 1 minute. I'm just confusing myself. Okay, this may be correct, but yeah, I'll just do one thing. Let's leave this. Just prove the first part. This should be similar. And I think it's also there in challenges and thrills. Similar question is there in the inequality portion. But we understand the context also. So try this question. And what was the other question I was thinking about? So, no, was there any other question I was thinking about? What did we just do? No. So just try this one for now. I will send more questions. Okay, you can try one more. This is interesting. So, yeah, how to divide. So this will be the precursor to what we do the next time. How to divide the number. Let's take any number, 72, into 5 parts, 5 integer. Now this can be said in terms of whatever chocolates and whatnot. Okay, integer, 5 positive integers. Okay, such that the product is maximum. Okay, so you want to break it into 5 parts: A1, A2, A3, A4, A5, in such a way that the product becomes as big as possible, right? Just to give an example, if I take the number 3, sorry, if I take the number 6 and if I want to divide it into 3 parts, then how should I divide so that the product becomes maximum? Obviously 2 plus 2 plus 2, right? You can see then the product becomes 8. If you divide it in some other way, like it is 6, product is 6, right? I mean, the sum is also 6, but that's not what I mean. If you divide it as 1 plus 1 plus 4, and the product is 4, right? So how to divide it so that the product becomes maximum? Is the question clear? Okay, and yeah, so this is another question that you should try. And now one more question. Given some numbers here, let's say Just give any numbers. Exact numbers don't matter. 5 numbers here. And then you have okay. So now you want to pair the numbers up between these two things. Okay. You want to take a number here and you want to multiply this with something, maybe this, and then take this number and multiply this with something else, maybe this. Take this, multiply with something else. Okay. So you want to, take one from the first set and one from the other set and multiply it. Okay. And do this for all the 5 pairs. And do it in such a way that the product maximizes. So the sum of the products. So what I mean is you can do something like this: 13 into 11 plus 1 into 12 plus 12 into 13. So you see I'm pairing it, plus 20 into 14 plus 5 into 15, right? And then you compute the, maybe you can calculate, or if for some reason, if you try all possible ways, I don't have a problem with that, but that will take a very long time. Okay, because there are so many ways, there are 5 factorial ways, right, to pair and so on. But yeah, there's one way, and there are many other ways, right, like this. So which way would give you the largest sum, the largest result? Okay. Yeah. Which one should you pair with? Which one you need to tell me? Like if I pair 13 with 11 and 1 with 12, and is that going to give me maximum, or is there some other? So you have to tell me which pairing will give. Okay. Now these things look like puzzles, but behind them are some very popular theorems, which I'm not saying now. Okay, I'm giving them in the form of just try them. And these are small cases, so maybe you can come up with other innovative ways to do it. Okay, so please try them. Okay, spend some time, because you may not be able to do, but if you spend some time, then that's the thing. Okay, so try these 3. I will try to take another class maybe on Saturday. This class and this batch. Okay then, please note it down, and I will share some videos which maybe I will recommend both of you to watch if you get time. Okay. Yeah. Otherwise, means it's not mandatory, but if you get time, you can do it. Okay. Okay then. Thank you.